All right, so I'm not sure how I bumped that and stopped it, but we'll keep going from where we're up to. So here we've got a list. We could use words to describe all points in the second quadrant. We could use a graph or a graph. I don't care how you say it. We can have a mapping. So what does that mapping show? The point 3 got mapped onto the point 1, or it got mapped onto the point 2. 5 in the input gets mapped onto 3 in the output, and finally 9 could be mapped onto 1, or 9 could be mapped onto 4. You can see 1, 2, 3, 4, 5 lines, 1, 2, 3, 4, 5 points. The mapping, or the set of coordinates, all showing relations. Okay, so that's what relations are. What's the most normal way that we see relations defined? We've got list, words, diagrams, whether that's a mapping or a graph. But the most common way is by a rule. And in particular, an equation. And this is the sort of relation that you've been dealing with for a bunch of years now and just haven't realized. Y equals 3x plus 5. That's a linear relation. Y equals x squared minus 2x plus 3. That's a quadratic relation. Anything of that sort of form is a relation. So we've got lots of different ways they can be defined, but all they are a set of points in my Cartesian plane with an x coordinate and a y coordinate is the way we usually talk about it. It could be that I've mapped all the points where R is a radius and A is the area. That would still be a relation. Why do I need to talk about relations with you now? Seems kind of strange. Well, it's so that I can give you a better definition of what a function is. Because probably our idea of a function in maths at the moment is just you put something into something and you get something out. Pretty much what I've described a relation as. But there's a mathematical distinction we need to make. Each point or value in the domain. Now, you may or may not have heard domain before. That's like the set of inputs. Or first elements in the ordered pairs. So I can think about it as the set of inputs or the set of first elements in the ordered pairs. Each point in the domain maps onto, so is turned into by the function, or corresponds with, or is in an ordered pair with. All different ways of saying the same thing. Each value that you put into the function maps onto, at most, one output value, or y value. So when I put a number in, when I put in an x value, there's only one possible answer I get, and I always get the same answer. That's a function. A function is reliable. If I put something into it, I know that I will always get the same answer when I put that first thing in. It's not always the case that that happens, but it is with a function. So an example of something that you've looked at that you might have thought was a function, but isn't a function, would be a circle. We've looked at circles before, right? Add a little bit more space. Oh, come back. E.g., x squared plus y squared equals 9. Bless you. Here's a diagram. X squared plus y squared equals 9. If x equals 1, what does y equal? And we can do it two ways. We can think about this algebraically first. Let's just do the algebra and see what we get. Replace x with 1, solve the equation, and tell me what y equals. So I'll give you 30 seconds to do that. We've only got 25 seconds left. You're going to be right, or you're going to be half right? You're going to be right. You see, Gary's going to be right. Or are you going to be half right? You're going to be half right? Did you have that written down before I wrote it? Good man. But you have the advantage of being beaten up last year for it. All right, so when I'm trying to solve this, 1 plus y squared equals 9, I am solving a quadratic equation. When I solve a quadratic equation, I set it equal to 0, so I'm going to subtract 9 from each side. Why are you doing it that way, Mr. Chewers? It takes longer. The square root of 8 is 2 root 2. I'm going to assume, I'll just tell you that now. You can go through the proof of it if you need to remind yourself. And we've got y equals negative 2 root 2 or y equals 2 root 2. If you only had the positive 2 root 2, I'm assuming it went like this. Which is dangerous. Try to avoid just square rooting each side of an equation if you can, because you eliminate that negative square root unless you are good enough to remember under the pressure of an exam, every time I'm doing that, I'm taking a positive and negative square root. You can still get it right, but it's a risk you're taking. Whereas if I set it equal to 0, use my favourite rule in maths, difference of 2 squares, I can't mess it up. I like to eliminate the opportunity to make errors, because why would I want to make a mistake? For maths, I know. You all knew how to get to an answer. You just don't want to give away one of the answers, give away a mark for nothing. If I was looking at it on the graph, when x equals 1, can you see that this line, x equals 1, cuts the circle in two places? That would be the point 1, negative 2 root 2. And the other point of intersection of that line, x equals 1, which is not really drawn to scale very well by me there, but you get the idea. 1 and 2 root 2. Those 2 points are sets, are ordered pairs that satisfy the set x squared plus y squared equals 9, the relation x squared plus y equals 9. But because when I put x in, there are 2 possible y values, that is a relation but not a function. Because a function is reliable. When I put in a value, I get the same answer. This is giving me 2 possible answers. So it's not a function. Now you needed to understand about functions and relations so I could talk about this next bit, which is y squared equals x and what it looks like. So that's all the background about functions and relations. Understanding that will help you make more sense of maths going forward in the next 2 years. Even though you probably won't be asked any specific questions about it. Maybe you will, maybe you won't. The last thing I will say is this little test here. See how a vertical line cut the graph of my relation twice? That's one way to check for a function very quickly. It's called the vertical line test. You have a vertical line cuts a relation more than once. Oh, my stylus is misbehaving. Then the relation is not a function. So it's effectively just an easy way of checking whether there's more than one possible answer for an x value. Even if it happens just once for the whole function, for the whole relation. If it only happens once, that's once too often. A function has to follow that rule absolutely every time. If I put in an x value, I get at most one y value. If I put in an x anywhere and I get more than one y value, it's no good. All right, so now we can start talking about the specifics of what we're dealing with today. The graph of y squared equals x. And I'll just make a little bit of a gap. Oh, look, and it ruined that picture on the right. Oh, I won't make a little bit of a gap. You'll just have to deal with it. Are we all happy that we know the parabola y equals x squared? The one on the left. So even if that was a little bit confusing, I've talked to you about relations and functions, and that's new. Now we're going to something nice and familiar. To find the inverse of a function, what we do is we reflect it. You swap the x and y coordinates. A function takes an x value, turns it into a y. To undo that, to do the inverse function, you have to take a y value and be able to turn it back into the x value. So one way you can do that, you can see there modelled in purple, is you swap the x and the y coordinates. And then you rearrange it to get back to y equals, and that tells you the inverse function. So we have the example here, y equals 2x. And you can see what we've done. To find the inverse, you let x equal 2y. So if I've got y equals 2x, the inverse function I would write something like, for the inverse, x equals 2y. And now I just want to rearrange it to solve so that it's in the form y equals again, because that's easy to deal with. And I don't mind whether you write it as a half x or x over 2. My preference is x over 2. I love written like that. But if you write half x, if that's your opposite of multiplying by 2, is multiplying by the reciprocal, multiplying by half, and you think about it that way, that's fine. You'll notice when you find an inverse, it's a reflection in the line y equals x. This mirror line is the line y equals x. And because I'm swapping x and y coordinates when I'm finding an inverse, because I'm going from a y back to an x, it has the effect of mirroring in the line y equals x. So if I was trying to find the inverse of y equals x squared, the first thing I'm going to do is I'm going to put my little mirror in here. Should I make it green so that it matches up with the other diagram? I probably should. Let's do that. Not drawn perfectly, but good enough. This is the line y equals x. And what I want to do is I want to mirror that graph. Well, At two particular points, there's not going to be any change. At both of the points listed there, and I didn't draw it perfectly, did I? It should be at 1, 1, so let's get rid of that one. At 0, 0, and 1, 1, when I switch the coordinates around, when I switch 0, 0 around, it's still going to be 0, 0. When I switch 1 and 1 around, it's still going to be 1 and 1. Those points aren't going to change. What other points could we find here? This would be 1.5, would be 2 1/4, would be about there somewhere. That would be the point. It's going to let me mark it. Stop doing that every time I try to put a dot. Okay, I give up. Pretend there's a dot. Oh, look, there we go. That point there, I'm trying to mark the point 1.5, so 3 over 2. And when I square that, I get 9 over 2 for y equals x squared. When I'm reflecting that, it's going to be the point 9 over 2 and 3 over 2. Dot. It's a reflection in the line y equals x. So when I want to draw what this looks like, it's going to go through about there somewhere. If I could draw that perfectly and symmetrically, that purple line there is the equation x equals y squared. It's a reflection of the line y equals x squared. If I take any point and I map it across the line y equals x, I'm getting the corresponding point. Obviously, I can't draw perfectly, so it didn't go exactly through it. But if you look at it in Desmos or on your graphics calculator, it would go through it perfectly. So that point was when x is -1 and I square it, I get to 1. Now it's the point, swap the coordinates around, 1, -1. Whoop, didn't write the 1. So, the pens are not as good. I got to get my old computer back. So, when you're finding an inverse, you switch the coordinates around. In this particular case, this inverse is not a function. Why is it not a function? Why is that purple line I've drawn not a function? Go, Karina. Yes, because the vertical line will cut it in more than one place. Look, I've even got vertical lines marked on there with the grid. Heaps of them are going through 2x, through the graph twice, aren't they? Not a function. But it is a relation. So, what this exercise is getting you to do, it sort of skips over all that. You've got a good interactive thing there where you can play around with that in your own time. But we want to look at, can I transform this relation, x equals y squared, about my plane, the same way I transform all my other functions. Move it up and down, move it left and right, stretch it and dilate it, or compress it. We want to be able to do the same things. And guess what? We can do the same things and they work the same way. You just have to switch on your brain and think a little bit and make sure you're getting them in the right way. I will sometimes mess these up because we don't do them as often. But that's okay. We still need to think about it. If I take a more general case, so y, instead of, remember our basic function was okay. Okay, so you want me to get rid of that? Parallel to the x-axis. And we want it as a b instead of an a. Okay, I don't think it matters too much, but it'll make it easier to fit in with our other notes. That's fine. So remember, we're starting off with y squared equals x. Let's just go through them one at a time. Multiplying the x values. You're going through your x values more quickly. It's going to dilate it or compress it parallel to your x-axis. That's what's happening every time. K value, shifting things up or down. Because it's happening inside the bracket, it's going in the opposite direction to what we usually do. You know when usually we just add a number at the end, it shifts it up? and take a number away at the end, it shifts it down. But when I do it just from the x, when I add it, it moves it to the left. And when I subtract it, it moves it to the right. When it's inside the brackets, it's going in the opposite direction. The same thing's happening with my k now. My k is inside the brackets with a y. The easy way for me to think about this is, I just think about what number would I put in for y to make that bracket equal 0. So that's going to take me to like my turning point of my original function. Oh, so I'd have to put in negative k for the y value to make that bracket equal 0. So my turning point is going to have negative k as a y value. What's my h value going to have? Well, that's in brackets again. So it's going to be negative h. And so you'll see where they've written it down. Oh, we haven't got to that yet. Let's do it down here. Let's actually have a look at an example. This will make it easy. So if I wanted to sketch that, what is going to make this value, y minus 4, to make that bracket equal 0, y would equal 4. I could think about it that way, or I could just say the translation 4 units, and it's the y value that's moving, so it's up. I could think about this x plus 3, and I could say what value of x would make it equal 0? Jumping to my answer, and it's negative 3. Or I can think about translated 3 units to the left. The general case that you'll see written in your textbook, and I think I've got it there for you. Let's make sure. I want to get the letters the same as the ones you use. They use H and K, don't they? Yeah. Y minus k squared equals a squared x minus h. So what I'm saying up there, the way I think about it when I'm just dealing with one thing at a time, if you wanted to, you could use that information and just use that definition as well. But if I wanted to sketch y minus 4 all squared equals x plus 3, you could do it on your calculators to confirm. We've said it's going to move 4 units up and 3 units to the left. We better check we're not lying to you, hey? Now you can follow along on your calculator, though it's a bit harder to sketch some of these things on your calculator. So we had y minus 4 squared equals x plus 3. As predicted, my turning point, it went 4 units up and 3 units to the left. So my turning point was at negative 3, 4. And so that's what the graph would look like. And we expected that to be the case. Let's go back and label those things again. We can snip that in and see that it was exactly what we expected. They've been a bit rude in the second question there, haven't they? Let's look at the first one again. We predicted it was going to move... Oh, why does it insert it quite so large? Let's make it a bit smaller there. We predicted it was going to translate 4 units up and 3 units left, and that's exactly what happened. From the turning point over here, it's gone 1, 2, 3, 4 units up, 1, 2, 3 units backwards, and the turning point's moved exactly where we thought it was going to. So when it's in that form, y minus k squared equals ax minus h, that works fine. Notice that the textbook actually says a squared there. it doesn't really matter. Finding the a value is something we're going to do. You have to do separately anyway, so it's not such a big deal. We'd use another point to find that. Whether you think about it as a squared or a isn't so important. But this one here, they've been a little bit rude to us, haven't they? Why is that a little bit more annoying? Because I wanted it in that y plus or minus a number form, didn't I? All squared. And I haven't got y plus or minus a number all squared. What am I going to have to do to get that into a nice perfect square? It's one of our favourite things to do in maths. Complete the square. Of course, we want to complete the square on that left-hand side so that I've got a y plus or minus a number in brackets. So when I'm completing the square, I'm thinking about making something that looks like a squared plus 2ab plus b squared, so I can simply call it a plus b all squared. Oh yeah, the stylus. I wonder if it's the battery already. Can't be the battery, it's brand new. Yeah. Here we go. I'll do it in blue just so we don't confuse our working. I'm trying to make a perfect square. On that left-hand side, I've got y squared plus 2 times y. What other number is going to make it equal to y? Well, it'd have to be a 1. So I've got to add on 1 squared. I'm cheating by adding on 1 squared, so I subtract 1 squared as well. And I've got my 2x plus 3 on the right-hand side. Y plus 1 all squared minus 1 equals 2x plus 3. I want to finish that off, don't I? I can add 1 to each side. Y plus 1 all squared equals 2x. I've added 1 to that other side, so it's plus 4. And the last thing I want to do is factorize that right-hand side. I just want it to be x plus a number inside that bracket. So what are the points where this relation is going to have a turning point? Where is it going to turn around? Well, we know the y value because it's y plus 1. It's happening inside the brackets. So it's going to be at negative 1. X has plus 2 inside the brackets. So it's going to shift 2 to the left. The turning point is going to be at negative 2. And so this relation is going to be a parabola turned on its side, and the turning point is going to be negative 2, negative 1. Let's see if it agrees with us. Y squared plus 2y equals 2x plus 3. Negative 2, negative 1. Guys, we did it. Isn't that nice? That is pretty nice.
When you do these questions, other than the turning point, what else do you think would be good information to include on these when you're in your exam? Intersect, exactly. So you do those the same way you'd always do, like x equals 0, like y equals 0, solve for the intersect.
Interestingly, what do you think would happen if I put a negative in front of that? If that a value was negative? Have a prediction. Just talk to the person next to you. Predict what's going to happen. Or in front of you or behind you. Talk to someone. Yes. What do we decide? Oh, it didn't put a negative in. Oh, I put an equals in. That was fun. Put my glasses on. Will we write my x values that were positive become negative and those that were negative become positive? Of course it's going to reflect it. And it reflects before the transformation, which is why it happened at that point. So putting a number in front, if it's negative, is going to reflect it. That will come up in the exercise. So basically everything in this little section is about transforming that y squared equals x by getting it into that form, y minus k all squared equals a squared x minus h, which we have here. It's relying on using that rule. Sometimes, last little thing, and it will lead into the next exercise because some of you will want to get into the next exercise as well, which is just looking at y equals root x or y equals negative root x. We want to be able to undo some things in maths, find inverse functions. In this particular case, the inverse is not a function. But we could think about it as two separate functions y equals root x and y equals negative root x. If we rearrange y squared equals x, there are two components that make up y squared equals x, that parabola turned on its side, opening to the right. There's the upper branch, y equals root x, and the lower branch, y equals negative root x. Then we can transform all of those just the way we've transformed every other function in maths. If I add a number at the end, it moves it up. If I add a number just to x, it moves it left or right. If I multiply by a number, it's going to dilate it vertically. If I multiply just x by a number, it's going to compress it horizontally. All those transformations are going to be the same. The reason we need to think about it like this is so that it still obeys all of my function rules, which is what we want. You have a few minutes left. See if you can sketch those. Just do a really quick sketch. I want you to identify the turning point. It takes algebra to find those intercepts. I'm not too worried about it now. Can you picture which way it's going to open up and where the turning point's going to be? If you can do that for those, check it on your graphics calculator so you get comfortable doing that. Or if you can't put it on your graphics calculator, use Desmos. You've got another 3 or 4 minutes. Do that now. I've got a couple of questions, so I'll answer those